On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at L'Hopital's rule example 7, and this is the 1 to the infinity power form. A little bit tricky what we have to do here, but just follow along and hopefully this will make some sense by the end of this video. We have f of x equals some stuff raised to a power. And let's find the limit of f of x as x gets close to 0. Well, let's see what we get. If we plug 0 into this right here, 1 plus 4 times 0, well, 4 times 0 is 0. 1 plus 0 is 1. And now let's look at the power. If we let x get real close to 0, right here, that exponent is 3 over a really small number. By small, I mean it is close to 0. Close to 0. What do I mean by that? Let's take 3 and let's divide by a really small number, like 0.001. All right, let's make it even closer to 0. And notice as I add more zeros up here, this number is getting closer and closer to 0, yet our number down here, our quotient, is getting bigger and bigger and bigger. Therefore, 3 over a really small number that's close to 0 is equal to infinity. Our exponent becomes infinity. Notice our form is 1 to the infinity power. That's exactly what we have right here. Now what we have to do with this particular problem is the following. Let's take this function here, 1 plus 4x all to the 3 over x power, and I'm setting it equal to y. And what I'm going to do with this is I'm going to take the natural log of both sides, as I've done right here in green. When we take the natural log of something raised to a power, we can pull that power down in front of the natural log. That's what we have right here. This is kind of a review of your college algebra days, hopefully. And then taking into consideration that the natural log of y, or natural log of anything, always has a base of e. If I take e and I raise it to all of this stuff, which is what I've done right here, e to that stuff, that is going to be equal to y. This is basically taking a natural log and converting it to an exponential. But what I want you to notice here is the following. Y is equal to this stuff, and y is equal to this stuff. Therefore, this stuff here and this stuff here, they have to be the same since y equals this and y equals this. With that said, what we want to focus on now really is let's find the limit as x approaches 0 of this thing. And whatever we get for that limit, we're going to come back and take e and raise it to that limit that we get. And once we do that, since all of this stuff here is equal to y, that will be the limit of our original function f of x. I know that's crazy, but now let's focus on this part right here. So let's find the limit as x approaches 0 of that exponent that we had. 3 over x, natural log of 1 plus 4x. And really what you can do with these types of problems when you have 1 to the infinity power, you can just take that exponent, pull it down, that's what I've done here, and then take the natural log of that other stuff, the base that we had here. I'm putting a star by this because when we come and get this limit at the end, remember, we want to take e and raise it to that power to find the limit of f of x, which is our main goal here. So let's see what we get. Let's plug in 0. If x is getting close to 0, remember we said that 3 over a really small number from earlier, that is equal to infinity, times, if we let x get close to 0 right here, that's 1 plus 4 times 0. Well, all of that's 1, and the natural log of 1 is 0. So now we have this form infinity times 0. Back in example 5, we covered that form where we had 0 times infinity. Go back and check out example 5, but I'm going to recap all of that with you right now as well. And what we did in example 5 is we wrote this as a numerator and denominator. So check this out. Limit, x approaches 0. Up top, I have 3 natural log of 1 plus 4x, and we already have this numerator-denominator thing set up for us because we have 3 over x. I just wrote my x in the denominator. Let's see what our limit is now if we let x get close to 0. Well, up here, we've already said that the natural log, when we plug 0 in here, this is the natural log of 1, and the natural log of 1 is 0 times 3. We still get 0 up top. And at the bottom, if we let x get close to 0, we have 0 at the bottom. There's our indeterminate form, which implies we can use L'Hopital's rule. All we have to do now is take the derivative of the top and the derivative of the bottom, and let's try to do this limit again. So using L'Hopital's rule, the limit as x approaches 0, the derivative of the bottom relatively quick, the derivative of x is 1, and now we have to apply the chain rule to this top part. We have 3 times the derivative of the natural log of this stuff is 1 over that stuff. So we have 1 over 1 plus 4x. But don't forget to apply the chain rule and come back and multiply by the derivative of this stuff. The derivative of 1 plus 4x is going to be 4. Now, let's clean this up and let's see if we can find a limit. So we have the limit, x gets close to 0. Since we're dividing by 1, we don't have to worry about all of that. And we can take 3 times 4, that's going to be 12 up top, and then we have this denominator of 1 plus 4x. And this is going to work out beautifully because if we let x get close to 0, 1 plus 4 times 0, 4 times 0, 0, plus 1, we get 1. Therefore, we have 12 over 1, which is equal to 12. But now let's not forget, this is the limit of this thing up here. Recall, whatever we get for that limit, the limit of our original f of x is going to be e to that limit. Therefore, the limit of f of x as x gets close to 0 is not going to be 12, it's going to be e to the 12th. That's the answer to our problem. And now let's verify this over in Desmos. So here's that crazy function graphed, f of x, and we want to let x get close to 0. We said our limit was e to the 12th. E to the 12th is a really big number, 162,754 point blah, blah, blah. So it's a really big number. Well, I'm going to come over here to Desmos, and I'm going to change my window. I don't care about -6 for my lowest x. Let's do like -0.1, and let's do +0.1 for our x max. For our y min, I'll leave it there, but our y max, let's make it about 170,000. And look, by me changing that window, this actually looks a lot better. And what we're concerned with is, as this x value gets close to 0, for example, my x value right now is 0.0023, pretty close to 0. Check out that y value, 154,065.982. As I get closer and closer and closer to 0, well, watch what happens when we hit 0. Did you see that? Undefined. But yet it's got a smooth curve, but it is undefined right there. But if I get real close, such as that spot right there, 0.0001 for x. That's doggone close to 0. Check out that y value, 162,364.752. I would say that's pretty doggone close to e to the 12th. I probably could change the window a little bit more to get it even closer for you, but I hope you get the idea here. Yes, as x gets close to 0, we are getting close to this e to the 12th power. And there you have it, a recap of some of your college algebra days and dealing with this 1 to the infinity power. And pretty much the shortcut is this. If you have 1 to the infinity, pull that exponent down, like I did here, take the natural log of that other stuff, work it all out. You're going to get some other indeterminate forms, which will ultimately and hopefully lead to L'Hopital's rule. And don't forget this, whatever that limit may be, the actual limit to your original problem, in this case f of x, it'll be e to that power. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.